In module 11, we're going to see how can we use Bayesian estimation to obtain the posterior density for our parameter given some data. So in other terms, when we have here our vector of random variable involved either in the resistance or solicitation model, we have used so far the posterior or the prior density for f of x, the joint density representing our knowledge of those random variables, and g of x being our limit state function. So we have here f of x, the joint density for x. We have the same thing represented as contour. We have the failure domain in pink. We have the limit state function in purple. Okay, we have the marginal density right here. So what we want to look at is when we don't know exactly what are the hyperparameters associated with this joint density for the random variable involved in our reliability problems. So when f of x has its parameters that are uncertain, how can we estimate them? So how can we estimate them? Through their prior and posterior density, where the posterior is basically a update of our prior using empirical data. So how can we use data in order to infer what are the parameters involved in the joint density for the random variables that are involved in or reliability analysis. So all of this seems to be convoluted. We're going to disentangle all of it in this module 11. So basically, how can we estimate the probability density for the parameters involved in f of x using empirical observations? So this is our third tool in our toolbox to use the result from reliability analysis, where we're going to see how can we integrate empirical observation into our reliability analysis through the estimation of the posterior density for the parameters involved in f of x. So first, we're going to see beyond this introduction at how can we characterize uncertainties and how does the influence the from their types, their reliability analysis. What are the types of observations we can use in order to estimate probability densities? How can we do that updating of our knowledge from prior to posterior using Bayes? So we're going to recap we're going to review what we've seen early on in the introductory material from the course. We're going to build upon it in order to update our knowledge using empirical observations. We're going to look at some example of applications, and we're going to see a quick trick that we can use to go around the difficulties we're going to see here, namely conjugate priors. So if we start with uncertainties, what are the categories of uncertainties and um, how do they influence the configuration of our reliability problem? So we can have two main types of categories for uncertainty. The first one is aleatory. It represents something that is intrinsic uncertainty, and it's considered as being irreducible. Okay, what it means is that if you collect more observation, you cannot reduce this type of uncertainty. This is really what characterizes aleatory uncertainty. The opposite end of the spectrum is epistemic uncertainty. Epistemic relates to lack of knowledge. These are uncertainties related to our state of the knowledge, and by definition, those are reducible, meaning we can collect further information in order to reduce those epistemic uncertainties. So what we're going to deal with in this module, or mostly related to that, what is epistemic uncertainty? Meaning those uncertainty source for which gathering additional information might help me reduce the uncertainty associated with them. So the random variable x are typically affected by both type of uncertainties, but not necessarily in the same context. So when we're in a design phase prior to building given structures, so we can say that all the uncertainties are considered as being aleatory. Why? Because we have sources such as intrinsic variability as well as uncertainty associated with the construction process. Since the structure is not built yet, we don't know exactly how the structure is going to be built. It's not made yet. The resistance has not been, if we can say, materialized. if we are in an analysis phase where we're looking at an existing structures, now we can have both type of uncertainty. Because for instance, in terms of material strength or what is the specific concrete mix that was used and pour in our foundation, all of those are materialized. We might not know exactly, but once the concrete is set, the concrete has a given resistance, whether we know it or not. So there can still be some part of intrinsic variability, but most of it is associated with lack of uncertainty. Most of it related to the specificities of the construction process as the structure has been built. So when we go in construction phase, everything mostly is aleatory, but as we build a structure and analyze existing structure, everything translates mostly into epistemic uncertainty, and that's where we can gather additional observation in order to reduce our uncertainty. For instance, we can go in the lab, we can take some concrete sample, break those samples, characterize, say, the strength or stiffness of the material that was used in building our structure. That may in turn reduce the uncertainty in our reliability analysis and thus hopefully reduce the failure probability. So we're going to look now at what are the type of observation we can use in order to better characterize the uncertainty associated with our random variables. So we're going to look at some definition, what types of qualificative we can associate with observation, and what are the uncertainties that are themselves associated with the observations. So let's consider a simple cylinder example where we would want to characterize the random variable x, describing, say, the strength of a concrete specimen. So what we would do if we have a larger sample, we would take smaller, say, core samples of that same batch, and we want to characterize what is x, the random variable, associated with that resistance. So f of x, x being the resistance, must be characterized by some parameters theta. And these are the parameters that describe the distribution of what the resistance for that concrete mix, say, could be. So x1 to xn's are realization from my resistance, meaning I can take different sample from a same concrete batch. If I go in the lab, they will all break at a given different resistance because the material that is heterogeneous like concrete could be considered as random because we know that we can take different sample from an exactly same batch and the heterogeneity at the inside the material will lead to slightly different resistances. So the question we want to ask here is, what are we doing when the parameters of such PDF are themselves unknown? What we want to do is that we want to use these realization of samples that we'll bring in the lab where we're going to test them. How does the result from the lab can inform us about what is the density for X? Okay, or what is the density for theta that is then going to translate into the density for X. So if we illustrate this, we have here the resistance of the concrete, what we ultimately are trying to characterize. So we know that this is represented by a probability distribution. So let's say here a normal or a log normal. So in this case, we want to characterize what is the mean and standard deviation of that resistance for my concrete. So what I want is to characterize using empirical evidence, what is going to be my distribution for the mean, what is going to be my empirical distribution or my distribution for sigma using empirical observation. And in this case, we want to characterize these two green distribution that in terms will help us characterize f of x. And to do this, we need to go into the notation of sigma and mu prime, which is going to present our prior parameters, and a double prime, which is going to represent our posterior parameters. Posterior meaning after being updated by data. And strictly speaking, we should speak of mu and sigma as parameters. So parameters in this case of f of x, the probability density representing my resistance x. And here, the mean of mu x, the standard deviation of mu x, would represent hyperparameters of mu x. Okay, parameters of parameters, we'll call them hyperparameters. Okay, here we can use parameters everywhere, but the strict term to describe those should have been hyperparameters. So now let's look at what qualificative we can use to describe our observations. So The end goal for us is to characterize the posterior density for theta knowing d, meaning the density of theta given that we've observed a collection of empirical observations. And these observations can be either in terms of type direct or indirect. A direct observation is that I'm directly going to seek, say, the stiffness of concrete. So what I'm going to do, I'm going to go in the lab and I'm going to directly use a press to measure the stiffness of my concrete. In that case, we would say this is a direct observation. An indirect observation would be, okay, the concrete is part of a structure. If I measure the displacement of the structure through the structural model, I could infer what should have been the stiffness of my material. So h of x would be the model of my structure, and the observation is indirect because now I cannot directly infer cannot directly measure the stiffness. I need to infer it through the model of the structure, thus the indirect label. My observation could either be exact or inexact. So when they're exact, whenever I observe a stiffness value, this is exactly the truth that I'm observing. In other case, I could have observations that are affected by uncertainties or errors. So in that case, the exact value of stiffness, whenever I measure it y, it's the exact value plus an observation error v. So, and in those cases, the error can be either additive, like x plus v, or multiplicative, x times v. Okay, so this is going to be an error that is scale dependent. So the higher, say, x is, the higher my observation error is. In this case, it's constant. No matter what x is, the observation error would be constant. In terms of qualificatives, we can have also direct measurements. So here nothing applies. This is business as usual. But we can have also upper or lower bound observation. In an upper bound observation, it means that what I observe, the reality is less than what I actually observe. So let's imagine you're trying to load test a structure, and while trying to apply load on the structure collapses. So you don't know exactly what is the strength of your structure. You just know it's less than the value before the collapse, but you didn't exactly characterize the strength of your structure. You characterize an upper bound, but the actual value is lesser than the value prior to collapse. The opposite is true if we have a lower bound. So imagine you go in the lab, you're trying to characterize the strength or the stiffness of a concrete sample, but the capacity, the force of your press is not enough to crush your sample. So if you're trying to characterize, say, its resistance. So if the force that your press can apply is not sufficient to break your sample, you're going to know at the end, if you reach the capacity of the press, that the strength of your sample is simply greater or equal to the value you apply on it. But you cannot characterize what is going to be its actual value. You will only have a lower bound on the capacity. You know it's no less than the force you apply, but you don't know exactly what is the strength of your sample. So if we look a little closer at the type of observation uncertainties. So there are two principal models, as we alluded to in the previous slide, for observation uncertainties. So the first one is additive errors. So we're going to say that our observation y is the reality x plus v and observation error. So in the case where x and v are normal, y is going to be v as well. It's going to be often convenient to use these models when everything is Gaussian. So it represents something like this. So if we have the reality x, y is going to be our observation uncertainty. So you can see that here we have a constant confidence region, no matter what is the value x. I remind you that we should read those confidence region as being vertically here, not perpendicular to my line here. Same thing apply for multiplicative observation. So we're going to say y equal x times v. So this is a convenient model when x and v are log normal because y is going to be log normal as well. So now what we have is an amount of uncertainty that depends upon the value of x. So the higher x is, the higher the uncertainty is going to be. So now if we want to include these concepts in order to update our prior knowledge for what these parameters could be using empirical observation. So to do this, we need to use Bayes' rule. Okay, we've covered this in the revision material we seen in the earlier module. Now we want to use this to update our prior using those observations. So we're going to review here the notation, Bayes theorem, and we're going to break it down into what we've seen earlier being the prior probability, the likelihood function, and the posterior probability. And we're going to see how each of those interact together. So f of x is, again, our probability density, either marginal or joint, that we're trying to characterize. Okay? In the previous module, we always look at this where we had an implicit definition or an implicit dependence upon the parameter theta. Now we want to make it explicit, so we're going to use that semicolon. So those parameter theta that are involved in defining that probability density are explicitly represented. F of y is the joint distribution for a set of n observations. So x is the quantity we're trying to characterize. Y is the density for the observations. So we can say that if x is a random variable, v is a random variable, y is going to be a random variable as well. We can have here an additive model. We can have here a multiplicative model, where in both cases, v represent the random variable describing the observation error. So if vi here is normal and vi is independent of vj for all I not equal to j, so basically any two observation error is going to be independent of each other. And in this case, if vi is again independent of vj and vj is log normal, so in such a case, we can describe the likelihood function, we can describe the prior, and by associating them, we can find the posterior PDF representing what is going to be f of theta, so the parameter we're looking for, given the data d. Okay, and from this, we can marginalize this information by building the joint between f of x given theta times f of theta given d. If I marginalize, meaning integrate over all possible values of theta, I'm going to get the posterior predictive for x given d. Okay, this is the same thing we applied in module 11 when we tried to use the linear approximation to obtain the predictive distribution for x. This is the same thing we're doing here. So what we want is now to explicitly characterize f of theta given d using Bayes' rule. So to do this, f of theta given d is what we call the posterior density for my parameter given the data. And we can obtain this from the formulation of the joint distribution between theta and d. And to express a joint distribution, it's going to be the product of a conditional times a marginal. So conditional probability of theta given d times marginal probability of data. The data of the probability, conditional probability of data given the parameters times the joint prior probability for the parameters. If I reorganize these terms to elucidate the posterior I'm looking for, I'm going to get Bayes' rule. So f prime prime or f prime given theta, these are equivalent notation. We're going to represent this in true Bayes' rule as the likelihood of observing my data d given the parameters times the prior knowledge for my parameter theta divided by my prior probability of observing the data, or my normalization constant or evidence. So as I said, f prime prime or f theta given d is my posterior probability density. This is what I'm looking for. This is what I'm trying to characterize using Bayes' rule. F of theta or f prime of theta is my prior probability density. F of d given theta is my likelihood, meaning what is my prior probability of observing data given the parameters. And the alternative notation is to use that L representation that would represent the likelihood of data given the data. But the way to read it or the way to explain it is always the same thing, is the prior probability of the data given the parameters. F of d is going to be my normalization constant. What is the probability of observing my data in the first place? And given that the posterior is a probability density, it must integrate to 1. And that's why we have that normalization constant, to make sure that if we integrate the numerator with respect to all possible values of theta, I'm going to get my f of d, my normalization constant, to ensure that this integral equals to 1. So how do I define my prior knowledge in the context of parameters? Okay, there are many ways. The first one is to use subjective knowledge. Okay, what is your expert judgment? What are physical constraints? What is known beforehand in the problem to characterize the parameters that are involved either in the solicitation or the resistance model? Then in the case where I don't have knowledge, I might want to use a diffuse prior. I don't want to add bias in my analysis. I want, say, to assume that all possible values for the mean are proportional to 1, meaning that are uniform in a range of domain. So I don't want to add much knowledge using my own subjectivity. So I might want to use diffuse prior that are, say, uniform or take other specific shapes. We can use iterative learning in a sense where, in the context of Bayes' rule, after seeing an observation and obtaining my posterior PDF, this posterior will become my prior for my next observation. So we can recursively update our knowledge so that after seeing a bunch of observation, the posterior I get becomes a prior for my next set of observation. So I can always accumulate knowledge recursively like this in a Bayesian setup. Now we've seen the prior. How do we define the likelihood function? The prior probability of observing the data conditional on a specific set of parameter value theta. This is how we read f of the given theta. If we want to represent this in the data, I have a vector of observation. So what is the prior probability of observing that random variable being equal to the specific set I have observed empirically, given a vector of parameter theta? So we can represent it directly like this by omitting the random variable, or in some references, they're going to write it like this. This is basically referring to the exact same thing. What is the likelihood of observing, say, y1, given the value that theta can take? So if we say that we have right now in our set D, a single observation y1, which is a realization of the additive observation process, y equal x, what we're trying to characterize, plus v, where v is a zero mean sigma v squared variance error process. And where x is a normal, where the parameters of that normal is mu x and sigma x squared, these are my two thetas. I'm trying to characterize the both using my observation y1. So in that case, my likelihood of observing y given theta is simply going to be the explicit formulation of my Gaussian PDF here. So it's going to be the normal with mean mu x, and as a variance, it's going to be the variance for y. So I'm going to sum the variance for x and the variance for v. So it's going to be sigma x plus sigma v to express the variance for y. Okay, this is a linear system involving these two Gaussians. If the observation process would be a multiplicative process like this, where x and v would be log normal, it would be similar, but now we would have the log normal instead of the normal formulation, where we're going to have the mu for the log space and the sum of the variance in, again, the log transform space. So now let's look at an example of a likelihood function. So let's assume that our observation that we got in the lab is y1 equal -1, which is a realization from that additive observation process. So f of x, the density we're trying to characterize, is the normal, for which we know what is the variance, but we don't know what is the mean. Okay, our parameter theta is going to be that mean value. So the observation error is a zero mean unit variance process. And we can express the likelihood of observing -1 using the formulation of the normal, where the mean is going to be mu x and the variance is going to be the sum of 2 squared plus 1 squared. This is what I have here in place of the variance. So mu x is going to be my parameter, y is going to be -1. So I can represent for all possible values of y and mu x this function here for my likelihood. In practice, once I have observed -1, I've only have access to the slice represented here by the red curve, which is here, which this curve represent how much each values of mu x is likely to be observed. No, sorry, how for each value of mu x, how likely was it to observe the observation -1? Okay, so this is that likelihood, what represent or what's going to weight what was the likelihood of observing y conditional on all my previous possible parameter of theta. So the thing is, what is the specificity of a likelihood? Is that a probability density will integrate to 1. Okay, that probability density of y given mu x, if I integrate under the area here, is going to give me 1. However, when I express it in the function of mu x, it won't integrate to 1 anymore. Okay, that's why it's specific to a likelihood. So the likelihood of mu x given y, so if we fix y, say equal -1, and we scan all possible values of mu x here, this is not gonna integrate to 1 anymore. It's not a probability density. It's just something that gives me how likely a value is given my observation. Then we don't necessarily have to have a direct observation. We can have, in this case, lower bound or upper bound. So in this case, we have a lower bound observation, meaning that the reality is greater than what we observe. So it's in the case where we have a press and the force that press can apply is not enough to break our sample. So if we have an observation that the observation is -1, we will have exactly the same parameters as before to characterize f of x and v. Now my likelihood is characterized by the complement of the CDF. So that complement of the CDF can be expressed here in terms of the error function. And if you plot, it's going to look like this. And for my observation y equal -1, this is what my likelihood, again, this doesn't integrate to 1, of course, this is what it would look like. So if y equal -1, you see that it's much more likely to have values of mu x that are above -1, and is much less likely to have values of mu x that are lesser than 5. In this case, that likelihood is fairly, like, it's not sharp. It's because I have observation error. If I would reduce this to 0, that would look like a sharp Dirac function centered around my observation, which would completely exclude the possible value below. So here it's not only a matter, sorry, of sigma v, a part of sigma v, and it's a part of in the inherent variability I have in f of x. If I would reduce both to 0, then I would have a sharp transition. Given that those are both uncertain, this is what caused that kind of smooth transition between the values or the likelihood of mu x. So if having a lower bound, I could have an upper bound in the case where I put some loading on a structure, the structure collapse. I don't know exactly what is the resistance of my structure. I know that the load applied is an upper bound upon that resistance. Using the same prior for f of x and v, now my likelihood is expressed as the CDF for f of y, where I can express in form of the error function. If again, I look at the curve here, which represent that surface is really the plot of that function. If I plug -1 here, my observation in that surface, I'm going to get that red curve here. That red curve represent, okay, if now I have an upper bound, if I observe -1, which is the dashed line here, I'm much more likely to have a mean that is lesser than -1 than I am to have a value higher than -1, say 5. Okay, so that's how, depending if I'm on direct observation, upper bound, lower bound, this likelihood function will tell me how much actual information there's about your parameter in the observation you gather. Now, if we dig a little deeper in the likelihood functions, f of y equal y given theta is, as I said earlier, the likelihood because it doesn't integrate to 1. So when I say integrate to 1, it's not with respect to y because it does integrate to 1 with respect to y. It doesn't integrate to 1 with respect to theta. So when we have multiple observation and all of them are independent, we can obtain directly the joint likelihood for a set of observation by taking the product of the marginal likelihood for each of those observations. But the problem is when doing so, we can quickly get 0 because of numerical inaccuracy. So in that case, a more robust practice is to take the log of my likelihood and to take the sum of the log likelihood and then take the exponential rather than try to do the product of several small numbers. So this is going to lead to an increased numerical robustness when computing the log likelihood. Then how do we compute our normalization constant? What is on the denominator of our Bayes rule? So to do this, we need to compute the integral of what we have on the numerator. So basically the expectation with respect to theta of my likelihood. Okay, because remember the expectation is the integral of the quantity as I'm taking the expectation on, weighted by what are the possible or the likelihood of the different value theta. If I try to do this with Monte Carlo sampling, my estimate for that normalization constant is going to be 1 over n, the number of sample, of my likelihood for a sample of theta times the probability of theta divided by my sampling density. So in the case where I use, say, a uniform distribution to take my samples, I would need to put 1 over b minus a, the probability density for uniform distribution in the denominator. If I want to use a simplified case where I'm going to take my samples in the prior probability density, prior over prior is going to cancel out, and I'm going to be left with that simple formulation, 1 over m, the number of samples I take, the sum over what was the likelihood of each of my observation in my dataset D, given the sample of parameter I've taken from the prior distribution from those parameters. But be careful, this procedure is simple. However, it's only going to work in a small number of dimensions because when we have a large number of dimensions, what happens is that our likelihood will look increasingly peak. And the more peak it is, it means that the information content is located in a very narrow space in our domain theta. So if we samples f of theta in our prior here, which is fairly diffuse, very few of those samples is going to end up being in that high probability content region. So it means that our sampling is going to be highly inefficient. We're going to use a really extremely high number of samples to obtain a good accuracy with our sampling. So if we look a little closer at our normalization constant, let's assume that y equal -1 is a realization of that additive observation process. We have f of x is normal. We still don't know what is mu x. We know the variance is 4. The parameters we're trying to characterize is mu x. We have, again, that same observation error described by a zero mean unit variance process. So we know that our prior, or we assume it's given that our prior as for mu x is a mean of 1 and standard deviation of 5. So if we use Monte Carlo to estimate our probability constant, we would get here using a million sample 0.0681. So now we can use this um, normalization constant in addition with the prior and the likelihood to characterize what is our posterior probability density. Again, for the exact same setup, we're trying to characterize this. We already defined what is the likelihood, what is the prior, what is the normalization constant. So if we point by point multiply the likelihood times the prior, divide by f of d, we would get that posterior probability density, which if we try to do the integral, it would integrate to 1. One issue that we have is that often in complex case, the posterior probability density is not going to be Gaussian. It's not going to have a clean closed form solution. So in those cases, what we can really do is that we can, instead of having that whole distribution, we can represent it as a normal, where we're going to simply compute what is going to be the moments of my posterior, namely the expected value and the variance for my parameters. So I remind you, the expected value is the weighted sum or the weighted integral of my parameter value weighted by, in this case, the posterior. In the case of variance, is going to be the parameter value minus its expected value square, weighted again by the posterior. So we can do these moment calculation using Monte Carlo. So for the expected value, we can say 1 over m, sum of all my m sample, theta I times what is my formulation here for my posterior. In the case where h of theta is my prior, is going to be simply the values of my likelihood for my samples theta I, divided by my normalization constant. If I want to characterize my posterior variance, variance is theta minus the value we will have computed here. So again, if h of theta is my prior, it would simplify to this. So each of the sample theta I minus the expected value computed here, square, times f of d given theta divided by my normalization constant. This is if I take my samples theta I in my prior. So in this case, if we want to be exact here, given that the expected value was computed here for using the same thing, M should be M minus 1. For practical purposes, it's not going to make a big difference because the number of samples we're going to take here is very large. So if we look at the limit, when the number of observations I'm going to collect will tend to infinity, if our problem is governed by epistemic uncertainty, what is going to happen is that the posterior probability density for my parameter given the knowledge is going to converge to what we call a direct, meaning a PDF where all the probability mass concentrate on a single value, the true value. So in that case, when we have infinitely many data points, we're going to see that all the uncertainty about our parameter is going to vanish and all the probability content is going to concentrate on a given value. In such a case, simply computing the empirical value for our parameter is going to lead to the true value, and the variance is going to tend to 0. Okay, so what it means, if you're trying to say to characterize the resistance of concrete, if you have access to a very large number of samples, you don't need to do Bayes. You can directly compute what is going to be the empirical average of your resistance for your large number, say 100 concrete samples. Then you're going to see that the the expected value you're going to get from that empirical average is going to directly correspond to what you would get using a full Bayesian analysis. However, we're going to see in the next example, when you have access only to a small number of samples, say 3 or 5, you can no longer do this, because if you do so, you're going to neglect the uncertainty that is caused by the fact that you have a low number of samples. Okay, so before looking at this, let's look at a quick summary of how can we use Monte Carlo sampling to perform Bayes. So if we have n observation in m samples from Monte Carlo taken from my prior knowledge of theta, I can compute or estimate my normalization constant using 1 over m, my number of samples, sum over all my samples of the product of my likelihood for my n dimension. If I want to compute the expected value for my posterior, I can do so using this, where each of the values of that I sample theta is going to be weighted by the product of the likelihood for my n observation divided by my normalization constant. I can do the same thing for my variance. So instead of using theta, it's going to be theta minus the expected value computed here. But be careful, this procedure is really naive and it's really simple. It's going to work for low dimensions. It's going to be highly inefficient and if you deal with higher dimensions. So let's look at some example of application for this Bayesian inference. So we're going to look at some introduction. We're going to look at nomenclature for our Bayesian updating. We're going to look at what is our prior knowledge for our problem. And we're going to look at two cases. A case where we're trying, in this case, to characterize the resistance of a concrete sample. What if we're using a press that has a capacity that is higher than the resistance of the concrete cylinder we're trying to characterize, or when the capacity is lesser? So we're going to add, in this case, a lower bound on the resistance of our sample. So we're again dealing with an example where we're trying to characterize the resistance of a concrete, where the reality, okay, we assume that the mean for my resistance is 42. The standard deviation for the resistance is 2 megapascal. I say this is a reality because I use here synthetic data, so I can fix those parameters. But what I'm going to assume for the remainder of the example is that these two are unknown. I'm only going to have access to realization of observations, and I'm going to see, can I retrieve these two values that are going to be unknown throughout the example? Okay. So the resistance is characterized by a log normal random variable, where these would be the two true parameter for that random variable, log normal random variable, which is the mean of the log of R and the standard deviation for the log of R, okay, in the log transform space. So we're trying to characterize what is going to be our posterior describing these two values, defined by the product of the likelihood times the prior for these two divided by my normalization constant. So again, if R is the resistance of my concrete described by a log normal, mu R and sigma R are the parameters describing the probability density of that resistance itself. So the mean and the standard deviation. The mean of mu R and the standard deviation of mu R, the prime describe that these are the prior knowledge or the prior quantities. I have the same thing. I have the prior quantities for the mean of sigma R, the standard deviation of sigma R. These are going to be what we call hyperparameters. So parameters of my prior knowledge for the parameter mu r and sigma r. Then I can have the same thing, but with the double prime indices. These will represent my posterior hyperparameters. So if we define my prior density for mu r and sigma r, assuming that both our knowledge for mu r and sigma r is independent, I can take the product of the marginal for the two, where mu r and sigma r are both going to be described by log normal random variables, where my prior information is that the mean for mu r is 45, the standard deviation for mu r is 7. The mean for sigma r is 5, the standard deviation for sigma r is 2. So in that case, we can go from the log transform space to the mean and standard deviation using these transformation function that we saw, if I'm not mistaken, in module 2. So the first case, we have a press that has a capacity that is larger than the resistance, say, of the concrete samples we're testing in the lab. So in that case, we're going to be able to directly characterize the resistance up to an observation error. So here, the observation error is additive, or it's multiplicative because it's going to be additive in the log transform space. So in the log transform space, because it's additive, it's going to be described by that normal, which means 0, and variance 0.01 square. My likelihood function is going to be a log normal, where I have the mean in the log space plus the sum of the variance in the log space. So sigma ln of r, what I'm looking, or what I'm trying to characterize, plus the variance of my observation error in, again, the log space. My likelihood, if I express this analytic formulation for my log normal PDF, it's going to look like this. I have yi, all my observations, mu of ln of r, my first parameter, sigma of ln r, my second parameters, and I take these likelihood, I take the product for my n observations. So the number of concrete sample I'm going to break in the lab. My normalization constant is simply the integral of whatever I have on the numerator. So if we look in terms of result, what would we get after breaking a single concrete sample in the lab? I go in the lab, I take one of those concrete cores, I compute what is going to be the strength in terms of megapascal. It would be, say, 39.7. The first graph here I'm going to see is going to be my prior probability density. Okay, it represents, with respect to mu r and sigma r, what was my prior knowledge for f of mu r and sigma r. Okay, the reality, because everything in here is synthetic data, would have been that red point. So you see that my prior knowledge is much more diffuse than what is the reality. So the reality is still possible, but it's not even close to the most likely value. Then I have my likelihood. Okay, if I express the likelihood of observing that specific realization of the resistance with respect to different values of mu r and sigma r. So if I plot my likelihood, it would look like this surface. If I multiply my prior times my likelihood, I divide my normalization constant, I would get this posterior density f prime prime, where you can see the most likely value a posteriori after observing my values of the resistance is not corresponding to the reality because I have too few observations to do so. And if we look at here, my posterior predictive, the reality for f of r. So basically the real probability density for r, if I would use the true parameter value I used to generate the samples here, it would be the blue curve. And what I have now, my predictive PDF, is much wider because I have a lot of uncertainty in my posterior here. So that posterior predictive is obtained by marginalizing, meaning integrating with respect to all the parameter value of theta in the conditional probability density of r given theta times my posterior that I have here. So after seeing one observation, I still have substantial uncertainty in my posterior as well as in my posterior predictive. If I collect an additional sample, so my second realization is 42 megapascal. You can see the prior doesn't change, but my likelihood is going to change. So my likelihood is going to become slightly more peaked, but when I have two observations. It's not yet corresponding my posterior to the true value, but it's concentrating the information a little more. If I have 5 samples, this is even more concentrated. We see that we're migrating or posterior towards the true value, and posterior predictive and the reality are starting to look closer. If I use 20 observations, if I use 20. So you see that now the posterior has almost collapsed on itself and aligns with the true value. and the posterior predictive and the reality are coinciding. My likelihood is highly peak. So this is how it illustrated. When you have lots of observation, I could have directly average what is the values of the resistance for my 20 samples, doing a full Bayesian analysis or just an empirical average. Since the uncertainty all vanish here, I would have get the same result. However, this is not true if you only have access to 2 or to 5 samples. All the uncertainty you have due to the fact you have a low number of samples need to be considered if you don't want to underestimate the uncertainty in your analysis and in the calculation of your failure probability. So in the limit case, when you have access to an infinite amount of data, as I said, the posterior is going to converge to a Dirac. So all the probability mass concentrated on a single point, such as here. So in that case, doing simply an empirical average is going to give you the same result as doing a full Bayesian analysis. And in this case, the posterior predictive is going to lead to the true distribution you're trying to characterize. So if we look at a second case where we would have, in this case, a lower bound for resistance, meaning that the press we're trying to crush or concrete with is not strong enough. So in that case, what we observe is a lower bound on our resistance. So now the log likelihood, the likelihood is going to be represented by the complement of our CDF. And now our likelihood looks like this. So you see, if I have a single observation where the resistance is, say, 35 megapascal, the limit of what my press can push on the concrete, I would exclude the lower value, but I wouldn't exclude at all what are going to be the higher value. If I take 2 samples, I can constrain a little more the value. If I use 5, if I use 10 samples, you can see that I can really exclude with high confidence the low value, but I still get no more information on the higher value. So inherently, lower or upper bound observation are going to contain less information than direct observation. So the last thing we're going to see are conjugate priors. So how can we bypass the need of doing sampling by using some analytical formulation to perform Bayesian updating? So we're going to see at what is the problem we're trying to solve, how do we define conjugate prior, and how can we apply it in practice? So when we're trying to apply this Bayes rule, computing that normalization constant involve an integral that can be extremely complex and costly to do. So when we have a large number of dimensions, doing this analytically becomes increasingly difficult. And when we have lots of dimensions, say more than 10, the basic Monte Carlo and naive Monte Carlo approach we saw earlier is definitely insufficient. So in this case, what we can do in terms of approximation, we can say we're going to neglect the uncertainty. We're only going to consider a point estimate at the most likely value. So we're going to treat Bayes as an optimization problem. This is good, but this is not conservative, and this is going to neglect the uncertainty. This is not something that is necessarily desirable. We can do a Laplace approximation. It consists in approximating our posterior for the parameters by a normal, where the mean of the normal is going to be the theta MLE obtained here, where we try to maximize the likelihood finding the most likely value of parameters. So this is going to be our mean. And the variance in the Laplace approximation is characterized by the inverse of the negative Asian for the log likelihood. Okay, I won't go into detail here of what is the theoretical justification for this, but this is a well-known approximation for the posterior covariance that can be evaluated relatively cheaply. And finally, we can do advanced Monte Carlo sampling that we're not going to cover in this module, but can be done using Markov chain Monte Carlo, and namely the Hamiltonian Monte Carlo method that would allow us with much higher efficiency to sample our posterior. But the other trick we're going to see here is one that is super cheap and very practical, namely the conjugate prior. So what is a conjugate prior? So for some couple of likelihood and prior, the posterior is part of the same family as the prior. Okay, so what does it allow us to do? Is that we're going to be able to do Bayesian updating to obtain that posterior using simple analytical formulation. So if we can go look on Wikipedia, you can see a big compendium of what are, if we look at conjugate prior, big compendium of what are all the possible case of conjugate prior distribution that you can use, for which you can do Bayesian updating analytically for very low computational cost. So in that case, the hyperparameter that we saw are the parameters that will describe the probability density that we're trying to characterize using empirical observations. So if we take a look at an example similar to what we saw earlier, so we want again to characterize the strength of a concrete. Let's suppose that we know that the standard deviation for the resistance in the log space is 0.05, our observation error as a process error of 0.01. In reality, we don't know what is the mean for the resistance. Okay, the reality is 42. We don't know this. We're going to try to see if we collect observation, can we retrieve that value? Okay, in that case, we're trying to model the resistance by a log normal random variable where we don't know exactly what is, we know what is the standard deviation for the log resistance. We don't know what is the mean. So we want to characterize here the likelihood. The prior for the mean for the prior for the mean of the log resistance is given by a normal in the log transform space, where we have as the mean of mu r 45 and the standard deviation of mu r 7. So we're trying to characterize, in this case, what is the posterior for our knowledge of the mean of the log of r. So in that case, we can use conjugate prior formulation in order to directly approximate these posterior hyperparameters using these two analytical formulation that can be found from the rules of the normal with known variance here. If we recopy those conjugate priors and we replace by the values we've already defined, n being the number of samples and yi being our observations, we would get the posterior predictive hyperparameters or the posterior hyperparameters for distribution of mean of ln of r and standard deviation for mean of ln of r. And we can use those to obtain our posterior predictive. So either in the log transform space or for directly characterizing our log normal distribution. So if we look empirically what it would look like, after seeing a single concrete specimen, we would get here our prior density for mu r. The reality is that line that we don't know. So we see that we have a fairly diffuse or wide range of possible value initially. This is our posterior after seeing one concrete samples. The posterior predictive, the posterior predictive is in red, the truth is in blue. If instead of I see one, I see two, this is how it would narrow down my knowledge. If I use 5, you can see that I have almost coinciding where my posterior correspond to my reality of 42 that I've defined earlier. If I have 10, I'm even more concentrated. So here, the advantage of those conjugate prior is that if I have this case where I have likelihood pairs of likelihood and prior distribution, as you can see in the compendium I presented earlier, you can directly do Bayesian inference very quickly and cheaply. So what Bayesian estimation allow us to do is to extract all the information there is in your data. Okay, so when you have infinitely many data, doing a Bayesian analysis or simply computing like summary statistics such as the empirical average is not going to make a difference. But in practice in civil engineering, we often have access only to a small number of samples. And in those cases, it is critical to perform Bayesian estimation in order to extract the maximum amount of information from your data and not being in a non-conservative case. So in the case of reliability analysis, the uncertainty we're trying to characterize are those associated with epistemic uncertainty, meaning those that are reducible. And what we're trying to characterize with those epistemic uncertainty is that posterior probability density for the parameters involved either in the resistance or the solicitation. So meaning I want to characterize the posterior for the parameters such as the mean, standard deviation of each of my random variables. The observation I can use to do so can be either direct or can be lower or upper bound observations. And in practice, I can use either Monte Carlo sampling or conjugate prior to perform that Bayesian estimation. So that concludes what we want to see on how can we use empirical data in order to update our knowledge for the prior distribution of the random variable involved either in the resistance or solicitation. The next thing we're going to see is how can we see important sampling in order to overcome some of the limitation we saw in the crude Monte Carlo we saw in module 4 by a method that is more efficient and that allow us to go a little further in terms of estimating our failure probability using more advanced sampling methods.